today we're going to take a look at a gas law. We're going to look at Charles' law. Charles' law investigates or states the relationship between the temperature and volume of a sample of gas when the pressure is held constant. So since it's a given sample of gas, the number of moles is constant. There's no gas coming in or out. And if we're using a constant pressure device to contain that gas, we can cool it or heat it and see what happens to the volume. So I have a very elaborate, complicated, constant pressure device here, a toy balloon. Now, a toy balloon, you may think, oh, it just gets harder to blow up as it gets bigger and you put more into it, but that's not really the case. Once you get past that first point of resistance on a balloon, it's not that much harder to continue putting gas into it. So through most of its volume, it stays fairly constant pressure, which is what we're looking for. So first we'll fill it with some exhaled air. Now let's change the temperature and see what happens to the volume of the air in this balloon. To change the temperature, I could stick it in a freezer, but that would be boring. So I think instead we're going to cool it using liquid nitrogen. Now any gas, if you get it cold enough, under high enough pressure, will turn into a liquid. Liquid or nitrogen gas, the gas that most of air is, it constitutes most of air, turns into a liquid if you refrigerate it under normal atmospheric pressure to about negative 195 degrees Celsius. That's very cold. Now, that's its boiling point. So inside this very insulated flask called a Dewar flask, I've got some liquid nitrogen. Let's see what happens when we pour it out. Well, it hits the hot surface. Remember, to this liquid nitrogen, this is very far above its boiling point. So it's like pouring water on a hot skillet. It immediately boils. Let's see what happens if we use this liquid nitrogen to cool down this sample of air. You might want to make a prediction first. We're decreasing the temperature. What do you think is going to happen to the volume? Wow. That volume seems to decrease pretty rapidly. You can see the balloon crumpling, taking up much less volume. Now, if when we get it cold, the volume gets smaller, perhaps when we get it warmer, the volume might increase again. So we see as the temperature increases back to room temperature, close to it, the volume goes back to the sample goes back to its original volume. So as we see, as the temperature decreases, the volume decreases. And as the temperature increases, the volume increases. We call that direct proportionality. So if one of them, if the temperature doubled on an absolute scale, like Kelvin's, we would expect the volume to double in an ideal gas.